All right, today we're talking about a technique called electrophoresis. And what is it? Well, it's this incredibly clever way scientists have figured out how to sort the absolute tiniest building blocks of life.
So, let me ask you this. Imagine you've got a smoothie, right? And your job is to pull out only the strawberry molecules. I mean, how on earth do you find one tiny ingredient in a mixture you literally cannot see?
Sounds pretty impossible, doesn't it? Well, that's the exact kind of problem scientists are up against every single day. Only they're not dealing with smoothies. They're working on a much, much smaller scale, with things like DNA and proteins.
So, what's their secret? How do they actually do it? Well, it all starts with a surprisingly simple but really powerful idea, what we're calling the electric push.
And that electric push brings us right to our key term for today, electrophoresis. Okay, so the formal definition sounds a little dense. It's the migration of charged particles through a solution under the influence of an external electrical field. Phew. But what does that really mean? In simple terms, you're just using electricity to make charged things move. That's it.
Okay, but a molecule's movement isn't just about that simple push. It's more like a cosmic tug-of-war between two opposing forces. So on one end of the rope, you've got the electrostatic force. That's the electric field pulling on the molecule's charge. But pulling back on the other end is the frictional force, which is basically just the drag from the liquid it's trying to move through.
And here's what that tug-of-war looks like in action. You can see the electric field is trying to pull that charged particle one way, but the medium it's in creates this drag that's constantly pulling it back. And whoever wins this battle, well, that's what determines exactly how fast and how far that little molecule is going to travel.
But here's the thing, just pushing and pulling isn't quite enough to get a really clean, precise sort. Scientists needed something, well, a bit more clever. They needed to build a molecular obstacle course.
And that was the big idea. The solution was to turn that medium, the stuff the molecules are traveling through, from just an open field into a really complex maze. And you know what? This one innovation is what makes electrophoresis such an incredibly powerful tool.
And that brings us to the most common version of this you'll see, which is called gel electrophoresis. So in this technique, that medium, that obstacle course, is a porous gel. It's basically a molecular sieve. A great way to think about it is like a sponge just with these teeny tiny microscopic holes that are perfectly designed to separate molecules based on nothing but their size. So here's what the actual setup looks like. You take your mixture of molecules, let's say it's a bunch of different sized pieces of DNA, and you carefully load them into these little pockets or wells at one end of the gel. Then you submerge the whole thing in a solution and hook it up to a power source.
All right, so here's where the magic happens. Step 1, you load your sample. Step 2, you flip the switch and apply the power. This creates a negative end and a positive end. Now, DNA happens to have a natural negative charge, so guess what? It gets pulled toward the positive side. But, and this is the whole point, as those DNA pieces move, they have to navigate that gel maze. The smaller molecules, they just zip right through the pores, no problem, and travel really far. But the bigger ones, they get tangled up, they struggle to get through, and they move much, much slower.
And what you're left with is this beautiful, clear separation. You can see these distinct bands that form in the gel. The ones way down at the bottom, the ones that traveled the farthest, those are your small, fast molecules, the low molecular weight ones. And the bands that are still up near the top, well, those are the big, slow ones. It's a perfect sort, based entirely on size. But, science is never quite that simple. This whole setup works great for something like DNA, but for other molecules, like proteins, well, there's a catch. We have to figure out a way to make absolutely sure we're only sorting by size.
Because think about it. What if a molecule's own natural charge gets in the way of the race? Right? I mean, what if you have a really big molecule that also has a super strong charge? It might actually move faster than a tiny molecule that only has a weak charge. And if that happens, poof, our whole size-based sorting system is ruined.
Well, luckily, there's a solution. And it's a truly ingenious technique called SDS Page. What it does is find a really clever way to isolate size and make it the one and only deciding factor in the race.
So what's the secret sauce here? It's a special detergent called SDS, that stands for sodium dodecyl sulfate. And it does two really important things. First, it makes all the proteins unfold from their complicated shapes. And second, it coats every single one of them with a uniform negative charge. And the bigger the protein, the more SDS sticks to it, which means the negative charge is perfectly proportional to its size. This really shows what's going on.
You can see how these different proteins, once they're treated with SDS, are all covered in this blanket of negative charge. It completely neutralizes whatever charge they had to begin with, and it gives every single protein the exact same charge to mass ratio. So what's the takeaway? The race isn't about charge anymore, it's now a pure head-to-head competition based only on size.
Okay, so this is all really amazing technology for a lab, right? But why should we care? What does it have to do with us? Well, let's take a look at how this technique goes from the lab bench and straight into our actual lives.
Well, for starters, the applications in medicine are just vast. I mean, it's used to diagnose everything from blood disorders like sickle cell anemia all the way to assessing your risk for heart disease. Doctors can use it to analyze pretty much anything: serum proteins, urine, even cerebral spinal fluid, all to look for those telltale signs of disease.
And it goes even deeper than that. We're talking about cutting-edge research, like genotyping proteins that are linked to Alzheimer's disease. We see it in forensics, for DNA and RNA analysis at crime scenes. It helps identify all sorts of genetic deficiencies. I mean, it is a fundamental cornerstone of entire fields like enzymology and immunology.
You know, one of our sources really just sums it up perfectly. It's a simple, rapid, and highly sensitive separation technique used in clinical laboratories. Simple, fast, and super sensitive. It's efficient, it's powerful, and for modern science, it's absolutely essential.
So when you step back and look at it, we've gone on this incredible journey. We started with just a simple concept, an electric push. That evolved into this sophisticated molecular optical course, and that in turn became a powerful tool that literally helps us read the code of life itself.
So really, the big takeaway is this. A technique like electrophoresis gives us this amazing window into the fundamental building blocks of biology, things that were totally invisible to us before. It's a testament to our ability to decode the world around us. And that leaves us with a pretty big question, doesn't it? Now that we can actually see the building blocks of life, what are we going to find next?